Good morning, everyone. Welcome to the EPOS Data Portal training event. As you noticed, we are recording this event for publishing on the EPOS channels later. So also people who are not connected yet, because we have around 90 registered participants, they will be able to see it later if they're interested. So we are starting the training now, and I will guide you through the EPOS Data Portal together with Harald. So my name is Jan Michalek. I work at the University of Bergen currently together with Harald. I'm seismologist by education, but mostly working on EPOS related activities and projects for the last years. We will guide you through the data portal, how it works, or what you can do with that. But before going there, I will give a brief introduction, also some background, so you understand why the EPOS has been developed and what are the major objectives of the whole initiative. So here is the agenda. We will have the short introduction of the EPOS ecosystem by me, then a live demonstration by Harald, and then we will have hands-on training, which I believe will be the most interesting part for you to understand how to actually access the portal, how everything is connected. We have prepared an exercise to guide you through an online form, so you will have tasks and questions to answer and through that we believe you will learn the basic operations you can do through the portal. Then we will have a walkthrough. So we will show you how actually those tasks could be completed, and at the end we will have discussion. Before going to EPOS portal itself, I would like to talk a bit about the open science, because this is a backbone of the whole initiative. So whatever data are being produced through public funding should be eventually made publicly available again for other researchers or even public. So EPOS is supporting that through building an interoperable platform for sharing the open data. But of course, in the future, we would like to include also the open source. The EPOS data portal itself is actually released as open source software, and also share the open methodology, which will lead eventually to open access and open educational resources as well. So the open science is the main philosophy behind EPOS. Open science has its own benefits and barriers. The benefits: you will have easier and timely access to data and scientific products as soon as they are released from the project. You can verify the data source. You can reproduce your science because the data is always available, and also the methods. And of course, it's efficient use of research resources, so you don't need to measure or repeat the test or area research if it has been already done before. And of course, it shares the methodologies and algorithms openly, again, speeding up the research and development. The barriers might be different. Might be barriers. For example, different standards and vocabularies, which might be difficult or requires an overhead. So making your data openly available, it creates an additional overhead for the data management, because you need to consider to understand the standards and vocabularies to use. Your data might be fragmented, which means you need to harmonize them also with other scientists or domain-specific standards. There might be a perceived issue with the intellectual property rights, because you might think, yes, I collected these data through my project, but again, as I mentioned earlier, if the project has been funded through the public funds, the data eventually should be released publicly as well. Of course, there might be some legal and ethical issues related to the data, and that also, again, as an overhead, because you need to sort it out before making the data available. Making data open also is related to making them fair, which means findable, accessible, interoperable, and reusable, and potentially also machine readable. So not only humans can interact with data, but also machines, which requires even more strict rules for integrating the metadata standards and vocabularies so the machines can actually understand what is what. The open and fair research data management in EPOS is very important since EPOS is built bottom up. So the scientific communities, we call them TCS, the thematic communities, are very center of our internal relations. So those are providing the data and services, and the central system is aggregating them together and making them visible, which requires collaboration among the scientific persons, the IT persons, the governance. It has governance components, and that's the recipe to open science. It requires engagement of the communities, harmonizing the data, processes, and standards to create infrastructure, and building such infrastructure which fits everyone. Doesn't mean that we have to accommodate all the different methods from all the domains. That's not possible. Technically, it's very demanding as well, but build an environment where people can do their research cross-disciplinary or multidisciplinary up to a certain stage. So we are, let's say, starting the chain. So if you want to start multidisciplinary work, you go to EPOS platform, and then from there you can decide whether it fits you or you need specific tools, but at least a very good starting point, because you can find all the publicly relevant data from the geoscience or the solid earth science community in there. So EPOS is moving towards global science with the mission to establish sustainable and long-term access to solid earth science data and services, integrating diverse European research infrastructures under a common federated framework. Here I want to highlight the federated because EPOS as such is not storing or collecting the data itself in any central system. We collect the metadata, which means the descriptions of the assets provided by the thematic communities. We have a central catalog, so we basically know where the data is. When the user goes to our platform, they make the request to the metadata, and then the system is redirecting the data request directly to the server where the data is. This approach has an advantage and disadvantage. The advantage is that you will have always the up to the date data. So what has been released by specific community through their services, it's all immediately visible also in the EPOS data portal. So we don't need to it does not require to do the harmonization of systems and uploading data somewhere. We just, as they are published, they are also visible through EPOS. The disadvantages, if any chains of the system breaks, you will not get the data. But at the same time, we have very good monitoring system in place, so we know what's happening, and if the service is down, the service providers are notified, and we are trying to make the system sustainable and reliable in long term. So the plan is to build a long-term infrastructure for providing solid earth science data. Here you see the EPOS timeline. So it haven't happened overnight or not even within a few years. It took almost 2 decades to build system we have now, with the main implementation phase starting in 2015, when the ideas actually started to materialize, leading to operational release of the platform in April 2023. And since then, we are operational. Of course, continuing developing the system, adding more services, engage new communities, and make it richer for the researchers. EPOS is not only a project, it's an European Research Infrastructure Consortium, which is a legal entity residing currently in Italy, with the principal task to establish and operate their research infrastructure. In the map, you see the current members, the active members, the observers, light green, and also countries which are included in the integration plan, of course, because we would like to integrate the whole Europe, but the governance issues need to be resolved before actually getting data and services from these areas. So the portal provides service and data discovery, visualization, and data retrieval. Currently, we have around 400 data and service providers around the whole Europe, with more than 800 terabytes of integrated data. Again, the data are connected, but not in one place. The services are currently, I think actually we have more than 284 because yesterday was a new production version released. I think we are close to 300 now. And the average weekly visitors number is around 180. And that's quite stable throughout the almost 2 years since the portal has been made public. How it actually works in EPOS, I will briefly guide you through the data flow or the integration. So it starts on the very left-hand side and with the national research infrastructures or data centers who are collecting and providing the data. Within EPOS, those are aggregated within thematic core services or thematic communities, shortly TCS. And we have currently 10 of those communities. You can read the names here. And each community is responsible for applying the standards, harmonizing the vocabularies, and making sure the services are following the standards within those communities before integrating to EPOS. Then we have an interoperability layer, which secures the communication between the central system and the thematic communities, which consists of metadata layer, which is mapping the data services to our catalog and allows then integration into the central database. So in the integrated core services or ICS as you see, has several layers. We have the data portal, the white, which is a very central part, which provides access to data products, software services, and potentially also the ICSD. This is the blue wedge on the right-hand side, which I'd say third-party services providing extended features, for example, HPC resources, visualization resources to the central system. And altogether, it's made and available for users, which are primarily scientists, but also IT experts, governments, private sector, or society. As I mentioned, we have 10 thematic core services or communities right now. Seismology, providing access to waveform data and catalogs of earthquakes, also earthquake hazard and risk products. The near-fall observatories, which are multidisciplinary observatories co-located with major large forts in Europe. They are providing seismological, geochemical, and geophysical data. Then we have GNSS data and products providing pan-European coverage with the GNSS data products and data itself. Volcano observations, again, multidisciplinary, providing observations from volcanoes within Europe. Those areas are Italy, Greece, then we have Iceland, of course, and some other volcanoes around the world. Satellite data are mostly focusing currently on INSAR data and data products, providing mostly geodynamically or high resolution data within the geodynamically active areas. Then we have geomagnetic observations, which is actually a network of global observations, providing geomagnetic data, models, indices, and events. And also we have magnetotelluric models and data from specific surveys around Europe. Anthropogenic community has a specific approach and sharing data as episodes for specific observations around mines, for example, or exploitation boreholes, or when you do pressurization and observe the, for example, earthquake distribution, changes of the environment around. So they have specific areas within Europe and also globally to provide data from such episodes. Geological information modeling is currently providing 4 different types of data: borehole, geological maps, 3D, 4D model access, and map of mineral resources. Multi-scale laboratories are focusing on analysis of rock samples of various types of analysis. So it's polymagnetic, magnetic, rock and melt physical properties, and so on. And the very recent or youngest community is tsunami community, providing tsunami data hazard and risk products, together with monitoring sea level around Europe. So now I will explain how it actually technically works. So on top of it, of this picture, you have the GUI, which we can compare to the tip of an iceberg. So that's what you will see today and what the user is normally interacting with. But what you don't see is the actually major work done underneath, which is a central system collecting the metadata and connecting all the other components like the ICSD with the interoperability layer, which is the metadata mapping, and standing all the thematic communities. So those are the base of EPOS, because without the communities we could not do anything. We can have a wonderful system, but without data it will be just empty. So the communities are providing the data and services to the whole system, to the user interface for you to be able to find them and use them. So here we have a screenshot, one of the previous versions of the portal. So you can see, you can plot many different layers together in the map view, but you can also analyze the data through the table and a graph view, which Harald will show shortly. Here I have just a plan about the future developments, which we currently have as a prototype. So we don't want to provide only access to data, but also provide virtual environment for data processing and analysis through Jupyter Notebooks. So here is a screenshot of a Jupyter Hub or Jupyter Lab, where you can deploy your code, your Python code, together with the data retrieved from the EPOS data portal. It's not public yet, it's not available, but that's the plan to have. So idea would be to go to the portal, find your data you want, find the example codes, which we will collect as well in our catalog, and then deploy them in a specific server as a virtual environment and access it remotely, run it there, do the analysis, and then download the results to your computer. The advantage would be if your computation requires heavy resources for, let's say, HPC or HTC, that might solve the problem. To run the software somewhere else, not on your local machine. And that will be also linked to machine learning and AI applications to have a heavy calculations tasks elsewhere, and then only focus on the results on your console or on your site. Again, it's not in production yet, but that's about to come soon. So that's my part, the introduction of the EPOS ecosystem. And now I will give word to Harald to guide you through the live demonstration of the EPOS data portal.
Thank you, Jan. I'm Harald. I'm a geologist working at the University of Bergen, mainly work on training, and I'll show you a demonstration right now. All right, so when you Google EPOS data portal, you'll be headed to the landing page here. And from here, you can press data access. And once within the portal, you'll be prompted with this one. You can toggle this off, or you can leave your email for notifications, or you can start a guided tour, which is mainly going to show what I'm going to show now. You can also press do not show again, and then it will be stored in cache until you refresh your cache. Okay, so I'll start with data here. On the left side, there's a pane called data. There's a number here in the yellow circle that is 298. And that's the amount of services we have. These are the 10 different thematic domains, core services, as Jan described, which are hosting all of the data. So the 298 data sets or services are within these categories. So, and then you also have the filters here. You can specify further coordinates or geolocation by country. You can specify what time range is set globally, and also to last month, week, day. If you just want to have data from one provider, like INGV or ESA, you can do so here, for example. And you can also specify what kind of data visualization you want to sort by. So for here it's map, table, and graph. You also have a free text search, which is acquiring the name and the data and the metadata. And there's also another search here for location that we're going to explore further. There's a new feature here with scientific examples, which has a collection of demos like the one I'm going to show you soon. So instead of configuring everything yourself, you can have pre-configured cases you can see here. So small description, the list of services, name of the case, and just press this one. And then also, if you have configured something here, without logging in, you can copy the URL to your clipboard. So if you have some kind of project you're working on, you can share the configuration you have made with colleagues. And you can also log in if you want it to be stored to the next time you are here. Within menu here, you can press About. So here you can read about EPOS, see the EPOS API, open source project, citation guides. Here, there's a guided tour, which is going to show you the GUI and how to configure. So mostly the stuff I'm going to show you. And video guides are here. So there are 3 of them, major ones, that are going to show you how to use the EPOS data portal. And we also have some statistics. And for the map itself, you can either use a scroll wheel on your mouse or 2 fingers on trackpad to zoom, or you can use the plus and the minus symbol here. We also have a layer and legend control tool up here. Right now, it's only the base map that is shown, but if you have some services, they will also be shown here. You can toggle things on or off, change the different backdrops here. But then we have a table view, and we also have a graph view. So I will just open a service. It says under the services here what kind of visualizations we have for that specific one. So when I add this to favorites, I press the star. And once it is loaded, you can see it on the map, like so. And then you can open in table view. So if there are many data points like here, you can press this one to find a specific one on the map. And then it will show you this marker pop-up for the specific event. And if you go from the other approach, you can toggle one of them like so, and then press view and table, and it will highlight the one in table for you. And within table, you can specify different columns to visualize the different data you have. You can sort by the different columns as so, and you can export the data as CSV. And for graph view, I will also show you briefly how it works. So if I go into GNSS, and then I will find some of the services that can be visualized as graph, like this one. So once this is selected, you see there's one service that can be visualized in graph view. And for GNSS, you have 3 different components, east, west, and up component. Yes, so now I'll show you a demonstration. I'll start by location search by entering Sicily, Italy. We'll zoom in here. I'll create a rectangular section, bounding box. You can either do so or typing it manually with 4 coordinates. Here we see a structure, and I want to investigate this one further. So I'll start with the remote sensing and INSAR data, line of sight displacement time series, and then it will load these TIFF images, as you can see, with these different colors. So to investigate what these colors represent, you go to Layer and Legend Control tool here, and then it will tell you, show the legend here, that the 0 on average per year is green. More than 2 centimeters of uplift or movement towards the satellite is purple, and more than 2 centimeters away, maybe indicating subsidence, would be red. So mainly there are multiple layers on this one. So to make it a little bit more tidy, we can toggle all of them off and inspect them individually. Like so. Let's see, set this one here. And if you see the text here, you can see that there are about 7 years of averaging for this specific image. So that would indicate that this area here is uplifting more than 2 centimeters on average per year. indicating this is the hotter region and the more active flank of the volcano, and this would be the subsiding cooler part in this period. So, okay, let's investigate more layers. So within the volcano domain, I can go to geological map of Etna volcano. And then I will overlay these ones. And if you want to look through it, and this will tell you the legend here of the different layers. You can make it more transparent if you want. And then also you can go into the specific regions, see what details there are. So like the different lithologies, the information, yeah, many metadata and some scientific data for this. And this service here will be bulk rock analysis. So indicating the geochemistry from the magma itself and specific time periods. And we'll tell you which one of the, I think, major four events and when the eruption was, and the sample type and the reference to the scientific paper is derived from. Okay, so if there are too many layers at once, you can toggle them off like so. And I'll show you a few more. So let's see if I go to geological information and modeling. I can open a geological map here from the EGDI. Then it will give me a geological map from here. I also can see what the colors represent here. And also from here, I can press the map and it will tell me about the lithologies from the area. Might be a bit slow now. I'll turn it up for now. And then I would go to earthquakes or modern earthquakes. Within the seismology domain here, parameters of modern earthquakes. And opening here, I can just adjust the different parameters. So set the minimum magnitude here to 3 for these last 27-ish years. And it will show me the distribution of earthquakes more than 3 in magnitude. So if it's difficult to see, you can change the different layout here. You can have this solid and you can have it in a different color if you want. So what preference you would like to visualize this. I'll set it to 4 to see if there's a trend of distribution for earthquakes in this area. Just to see the stronger ones. Well, it seems to be more active in the eastern part of the volcano, at least to me. And for the last one, I will show GNSS stations and products. And let's go from there. Let's see. And this S here indicates the station that is located here. There's a 9-symbol code I will have to copy. And having some information about the provider, it would be Italy or Sicily. So we'll find a daily position time series from INGV, put it to favorites, and then input the code. I'll just copy it and then press apply. And once I've done this and it has loaded, I can go to graph view. And there I want to investigate the up component. So to use the same period of time as the ends are, let's set it to roughly 2016 to 2021. And there seems to be a trend that is uprising in this area ever so slightly. And there are some variations, maybe seasonal, maybe it's water, maybe it's something else. But on average, it is almost green, but it's slightly yellow. So you can see that can correspond with the inside data from the same period of time. Yes, so that is my demo, and I hope it was helpful, and you will soon have your hands-on training. Thank you.
Hello, everyone. So we are back. As I asked you earlier, please go and submit the form, even though we haven't managed all the tasks. But I believe you managed to complete the task because it were not that many. I will start sharing my screen now, and I will guide you through the scientific user story we prepared for you. So I'm starting with a fresh view with nothing basic as you would arrive at the portal, and we'll follow the procedure step by step. So we are about to explore earthquake data, specifically moment tensor catalog, the fault maps, and geological maps when in Santorini area. So the first point was to go to Santorini. So you can use this magnifying glass in the map to locate the Santorini island. So if I type Santorini, actually see there are many different places called Santorini, but if I specify GRC, which is in Greece, it brings me to this area, to the island. I zoom out a bit to see it. Then, because I want to get data from this area, I will specify the bounding box by setting the coordinates. You can draw the bounding box by hand, but then we might have different results depending on what you actually do. So for that reason, we put specific numbers here. So it starts, the north is 37, south is the 36. And then we go from 24 to 27 east and approve. So it gives me slightly different area, but still area of interest around the island. Then to specify the start date as a global filter. So whatever I apply here, it applies actually to the whole filter of all the services. So I set the click in the map 1st of January 2025 and click apply, and it's already filtering also the list of services and applying the temporal range to services which support the temporal selection. So I should search for fault using the free text search. So I go to free text, type fault and hit enter. I got 20 results in total, and the task tells me to navigate to seismology and look for European Fault Source 2020 WMS service. So it's actually the first one. Before going there, where I can select the service, starts loading. While it's loading, I can click the small I, which we forgot to explain. The small I provides details about the service. So you can find the name, domain, categories, description, what it actually shows, how the product has been made, the spatial coverage, temporal coverage, if defined, license, keywords with the definitions, also the quality assurance, who is the data provider. It can be multiple, where to find more information about the service, and also the service details itself. Probably the most important or interesting for you might be the service documentation and service endpoint. So where to actually find the data itself. So now the service content has been loaded. So you see we have red lines shown in the map. This is WMS service, so you can click on any of those, and you see basic information about the fault. So it has an ID and break values like minimum, average, and maximum, fault type, which would be actually the one for the question 1.1. So the fault type is N in this, and all the faults, I believe if I click here and explore the legend of the, so all of these type red lines are of normal type. So I can see either through the legend or if I click on the map on a specific line, because all are red, so it doesn't matter which one I click, it brings me in the legend fault type N, which is normal. So the right answer should be normal in the question 1.1. Okay, go to the next task. The second task is about earthquakes. So now I should remove the of clear this free text search. So I click the X next to the fault. As you see, the selected service stays in my favorites. So in my favorites, I have still the one from the first task. Now I need to search for moment tensor. Sorry for the typo. I haven't noticed that until Philip notified me through chat. But if I search even for a moment and hit enter, I should get service. Okay. Yeah, I have to switch to the category of the seismology, and then I have multiple services. Some are map services, but I'm interested in the moment tensor data for modern earthquakes 2030 to present. Yes, this one. So again, I click the star, which it does two things. When I click the service, it immediately connects to the service and made the default request, the default query specified for this service. At the same time, it adds to my favorites. So now again, if I switch to my favorites, I see those two services. Then I want to reconfigure that service because the task was saying I should change the attribute, limit the number of output entries. So by default, the number of entries is 250. If I want to see more earthquakes, I can put 1000, which is actually the upper limit. So if I put 1001, it's actually showing unknown validation error, which means I'm now above the limit. So 1000 is the highest number I can apply or request data for. So if I click apply, it now made a new request to the moment tensor service and getting the data, converting them on the fly, and showing them in the map. So now if I then go up to the service description again, I can click the table, which opens the table. I can expand it a bit to see more. I can also choose to see more entries, more results per page. I can go for 50. And I can also add more attributes to show. So the point 2 in the task 2 was export a list of earthquakes from the table view and also from the download menu. So from the table view, it's easy. I can just click the export data and it immediately export whatever is selected in the table. If you want to add more, you can also check all the different columns. You can add more information. Okay, I will just disable strike break. I will already enable the percentage DC, ISO, and CLVD because that was we will need that for the later task. So by default, only first 8 columns are shown, but you can change that later. So we have the export through the table we did. The second question through the download menu. Again, this we forgot to explain during the demo, but if you scroll down through the service at the very bottom, you have three buttons, and one of them is download. If I click the download, it brings a new pop-up window with the citation first, so how to cite. So if you want to use the data in any publication, here is the citation you should use. You can also copy the clipboard. And more important is the data, or interesting for you. You can choose data in different formats, QuakeML, text, JSON, or the converted version for plotting in the portal, which is the GeoJSON specific format. But the task is asking for the text version, so I click the download. I can also copy URL, which will not make the direct request, but it copies the URL of that request if I click the download. So I can copy this one and save somewhere else to be used either in my scripts or anywhere for reference, so I know which request I was making for the data. I will click the download. Again, it's presenting me the reference or citation, and also it shows the data in the download menu. So now I have both versions, the CSV and moment tensor data. If I open it, probably you don't see it now because I'm not sharing that window, but I see the content in the notepad, and it gives all the basic information presented in the table view. Now going to the question 2.1. When was the latest earthquake with a magnitude above 5? And that you can identify in the table view. So to be able to see the latest earthquake above 5 magnitude, I will first sort them by magnitude. So I click the magnitude value twice. So it changed the order. So it's now sorted from the largest magnitude. And then if I go, okay, now I don't see the date clearly, so I will remove these three columns, which I will need actually in the next step. But here I can see what was the latest about magnitude 5. So these are starting, magnitude 5 and larger are starting here. And the most recent I see is the 18th of February. Probably, yeah, the 18th of February is the latest. So that was actually the last option in the pre-selected values in the questionnaire. So going to question 2.2, did you manage to download? Yeah, well, then you just check whatever is relevant for you. And then I'm going to question 2.3. What is the most frequent focal mechanism in the dense cluster of earthquakes in the central area? I will now go back to the map view and zoom in. For seismologists, it's probably straightforward to understand what is the faulting type. For those who are not that familiar with it, I put some hints. So normal faulting should have the kind of white part in the middle. The thrust faulting is, I'm looking for it. Some of them should have the red part in the middle. It's difficult to see. I think there are some, but not really many. And strike slip has the cross-cutting fault plane somewhere in the center. So like maybe like this this particular earthquake. These two actually are strike slip. So as you see, most of them are of normal type faulting here. What is interesting here that the orientation of the fault plane, I mean, we have, let's say, two different solutions for each focal mechanism. So we don't know which fault plane it is, I mean, which dip it has, but we know that the strike is approximately northwest southeast, which is perpendicular to the indicated fault, the known fault in the area. So that's very interesting. So it's not parallel but perpendicular to that. So that was the question 2.3. It's a normal folding. The question 2.4, that requires a bit knowledge of the moment tensors, what it actually means. Task or the question is about enabling and investigating the percentage, the double couple, the DC, the isometric volume changes, and CLVD, which is compensated linear vector dipole. So those three are always part of the moment tensor solution, and the percentage, all three parts together should give 100%. So the ratio between them gives you an idea about the physics of the focal mechanism. So as you see here, many of the earthquakes, especially the large ones, have very large percentage of DC, which is double coupled. So it's let's say pure shear, almost pure shear focal mechanisms. But there are also some earthquakes which have also quite considerable high CLVD part. The isometric reflects basically the volumetric changes, either explosion or in deflation. So it means it goes either up or down, like together, or expanding. While the CLVD is compensated linear vector dipole, which is there's a pressing force from one side, but there's also expansion in another direction. That is actually an indicator of a magma intrusion. So if I search or sort the data by the CLVD component, I see that many earthquakes actually have significant part of CLVD above even 80%, which might be a good indication that there is actually ongoing magmatic intrusion in this area. So that would be the question 2.4. And now I'm moving to the last task. Okay. Which is about the geology information modeling. Again, I need to remove the free text search, and then I should be able to find the geological map here. So I have the geological feature view service to be added to my favorites. So I, again, click the star, or collapse the table, and wait until the data is loaded. So again, in the background, the server is connecting to the EGDI service, getting the data and plotting them as a new layer in the map. So I have, let's say, 3 layers now showing at the same time. Question 3.1, what lithology is the bright blue color in the map and what it represents? So again, it's not that tightly linked to the actual scientific use case, just to learn, to teach you how to interact with the layers. So you can click on the map in the area of interest, and then you find that the light blue is marble, or it might be actually limestone as well. Depends which particular point you click. Okay, so that's the answer. And then we also had a bonus task, number 4. If you could display Hellenic subduction zone in map, as you see at the screenshot as a hint. One way to do that is to simply type subduction and see what results we will get back. So I use the pretext search, type subduction, and then I see that I have in Seismology, I have 5 services. Actually, no other communities providing data for that. And then I have service WFS, having a subduction word in the title. It's another one as WFS for the meshes. So I would go for this one. Again, I'll put it to my favorites. Now it's connecting to the service and plotting it as a new layer. Maybe I can change the color of the line so they don't interfere with the cluster faults loaded earlier. So I will choose a green color, maybe slightly brighter. Yes, okay, maybe a bit thinner lines. So I can adjust the view, and now I have all the tasks completed. For the subtraction, you can again click on the lines to understand what they represent, and it gives you the depth of the subduction zone in that particular area. In this case, it's 50 kilometers. So this was the brief summary of the tasks and a walkthrough. I will pause the recording now, and I think we can go to the questions and answers.